Hello everyone. In this video, we will be discussing series solutions of ordinary differential equations, but this is quite long, so I decided to just divide the presentations or the video into smaller presentations following a specific step for the calculation or for finding the specific solution to a particular ordinary differential equation. Now, the general form of the ordinary differential equation for a linear second order homogeneous ODE is given by this equation. We have d squared of y with respect to x, whereas we know y is the dependent variable and x is the independent variable, plus px, first derivative of our dependent variable y with respect to x, plus q as a function of x, y is equal to 0. And in many mathematics and physics books, this could be written in this form. We have a y double prime plus b y prime plus cy is equal to 0. Now, in solving this ordinary differential equation, there are many techniques. But in our series of videos in solving this ODE, we will only be introducing two techniques. We have by substitution of an exponential ansatz, and secondly through the so-called Frobenius method. But in this first video, what I will be discussing is just the method of using or of substituting an exponential ansatz. Now, from the term itself, exponential ansatz, to solve this ordinary differential equation, we propose an exponential ansatz of the form y is equal to e to the px. Now, you might be wondering the choice of this exponential ansatz, particularly the exponent px. Do not be confused with this, because this might change depending on the particular ordinary differential equation that you are trying to solve. Say, for instance, the general form of our ODE in this presentation is this, which we can see that the independent variable is x. And this is the reason why our exponential ansatz in this presentation is given by e to the px. That is y as a function of x. But in certain cases, such as in the case of a harmonic oscillator, where the independent variable is the time, we just have to change our exponential ansatz in this case, such that our dependent variable y is as a function of our independent variable t in that case. Having said that, we will be using, meanwhile, this exponential ansatz for purposes of this discussion, wherein our y, which is the dependent variable, is as a function of x. Thus, if we want to solve this equation, we just have to get the derivatives of our exponential ansatz. In this case, y prime is equal to dy over dx, which is simply just p e to the px. Of course, we will also be solving y double prime, or just the second derivative of our y, which is the dependent variable with respect to x, and this is just equal to p squared e to the px. Having solved the first and second derivatives, and having known the exponential ansatz, we just have to substitute those derivatives with our general form of the ordinary differential equation. As we know, the first term here is just y double prime. We have a, copy a, and then we have y double prime plus b, that's b, y prime plus c, and then we have our original exponential ansatz, which is e to the px, and this is equal to 0 because this is a homogeneous ordinary differential equation. We can see a common term in this case, that is, we can divide both sides by e to the px, so that we are left with a quadratic equation given by ap squared plus bp plus c is equal to 0. And we know in this case that if we want to solve the roots of this quadratic equation, we have two possible values for p by calculating the roots using the quadratic formula. And since we have two possible values, the values could be positive or negative, and sometimes we arrive at an imaginary value or at a complex number. So there are many cases upon which we base the general form of our ordinary differential equation depending on the roots that we calculate. And these are the cases. Firstly, if there are two real roots such that p1 and p2 are all real, then our general solution for our ordinary differential equation is given by this equation. We have y is equal to c1 e to the p1x plus c2 e to the p2x. Again, if the roots that we calculate are all real roots, then this is our general solution. If one of the roots is positive, such that p1 is greater than 0 or p2 is greater than 0, then the general solution is an exponentially growing solution. This is our case 3. When p1 is less than 0 and p2 is also less than 0, then we have the overdamped solution, which is described now by this graph in this case. We have, finally, for the fourth case, if there are two complex conjugate roots, we make use of the Euler's identity. That is, if both the roots could be expressed in terms of this equation, r plus or minus iq, where r is the real root, and then we have the imaginary part of the equation. So the general solution is actually a general oscillatory or underdamped solution. And that is given by this equation. We have y as a function of x equals e to the rx times the quantity c1 cosine qx plus c2 sine qx. Now, in our next video, we will try to apply our method, that is the substitution of an exponential ansatz to the linear oscillator equation. In this case, our independent variable is t, and we can see that the form of our exponential ansatz shall also be as a function of time, and then we will see which of the four cases shall we use for the general solution of this linear oscillator equation.